Right now, as you read these words, you are hurtling through a region of space so vast and so empty that the human mind has no framework to contain it. Not metaphorically empty, not poetically empty, measurably, quantifiably, catastrophically empty. The volume of space surrounding your position in the cosmos, extending outward in every direction for 1 billion light-years, contains roughly 20% fewer galaxies than it should. 1 in every 5 galaxies that the laws of physics and the history of the universe predict should exist in your neighborhood is simply not there, gone, absent, missing from the ledger without explanation, without drama, without any visible sign that anything was ever taken. That deficit stretches in every direction simultaneously, north, south, east, west, toward every constellation you have ever named and every patch of sky you have ever ignored. It does not thin out as you look in certain directions and deepen in others. It is uniform, spherical, centered with uncomfortable precision approximately on us. You are living inside the largest confirmed cosmic void in the observable universe. But here is what makes this discovery so much more unsettling than the mere fact of living inside an enormous hole in space. The void did not announce itself. It left no mark on the night sky that any human observer could perceive with their eyes or their telescopes, or their most sensitive instruments for most of the history of astronomy. The stars above you look exactly as they would if the void did not exist. The galaxies catalogued across centuries of careful observation showed no obvious sign of the surrounding emptiness. The void hid itself inside the most fundamental assumption of modern science, the assumption that wherever you happen to stand in the cosmos, your view of the universe is representative, that your measurements reflect universal properties, that the space surrounding you is at sufficiently large scales typical. That assumption may be wrong, and if it is wrong, then nearly every number cosmologists have spent decades refining the expansion rate of the universe, the age of the cosmos, the balance of forces that determines the fate of all matter and energy. Every one of those numbers carries an error. We have only recently begun to understand an error introduced not by faulty instruments or careless mathematics, but by our location, by the particular emptiness we happen to inhabit. This is the story of cosmic voids, of how astronomers discovered that the universe is structured not around the galaxies and clusters we celebrate, but around the vast dark spaces between them, of how the largest such space turned out to surround us, completely extending so far in every direction that we spent decades staring at the cosmos without realizing we were looking at it through the distorting lens of an enormous absence, and of what that absence means, not just for the measurements cosmologists make in their observatories, but for the nature of the universe itself, for where it came from, what it is made of, and where it is inexorably going. The answer when it arrives in full is not comforting. It is not the kind of knowledge that makes you feel at home in the cosmos. It is the kind of knowledge that makes you realize the cosmos was never what you thought it was. That the universe you picture when you close your eyes and imagine deep space filled with galaxies and nebulae, and the warm, steady light of hundreds of billions of stars, is not what the universe actually looks like. It is what the universe looks like in the rare, temporary, luminous exceptions to its dominant condition. The dominant condition is the void. If you find yourself drawn to journeys that permanently alter how you see reality, do me a small favor and hit that like button and subscribe. It genuinely helps this channel reach more people, and it allows content like this to keep finding its way to the minds that need it most. Now, get comfortable, because where we are going will take some time to reach, and the destination, like the void itself, is larger than you expect. Let's begin. For most of recorded human history, the universe appeared full. This is the first thing you need to understand, and the first thing you need to discard. The intuition that the cosmos is crowded with matter is not foolish. It is the natural conclusion of every observation available to the naked eye and to every telescope built before the middle of the 20th century. Look up on a clear night far from city lights, and the sky appears saturated with stars, layer upon layer of them, extending in every direction. The Milky Way itself, a luminous band of accumulated stellar light, so dense it seems almost solid against the dark. The sky does not suggest emptiness. It suggests abundance. When astronomers began pointing instruments at the sky in the 17th and 18th centuries, the impression only deepened. Every increase in telescope aperture revealed more objects. Faint smudges resolved into spiral nebulae. Spirals revealed themselves to be entire galaxies, island universes, containing hundreds of billions of stars each, and there were millions of them stretching in every direction to the limits of detection. By the early 20th century, after Edwin Hubble had confirmed in 1924 that the Andromeda Nebula was not a nearby cloud of gas, but a galaxy lying approximately 2.5 million light-years from our own, the universe had expanded in the human imagination from a single galaxy to an apparently infinite collection of them, and they seemed to be everywhere. The working assumption embedded in cosmological thinking was clean and elegant and seemed well supported by observation. At large enough scales, the universe was smooth. Matter distributed itself uniformly across space, with local variations. Of course, galaxies clustering here, a sparse region there, but nothing systematic, nothing structural, nothing that would make one region of the cosmos fundamentally different from another. This principle had a formal name, the cosmological principle. It stated that the universe viewed from any location and in any direction across sufficiently large scales would appear the same, homogeneous, isotropic, the same recipe everywhere always. It was more than a convenient assumption. It was the load-bearing wall of modern cosmology. Every equation describing cosmic expansion depended on it. Every model of structure formation assumed it. Every attempt to extract the fundamental parameters of the universe from telescope observations rested on the premise that the numbers measured from Earth reflected universal truths, not local accidents. The cosmological principle was not frequently examined or questioned in any serious way. It was simply there, as invisible and as essential as the air inside a building. Nobody noticed it because nobody thought to look for it. The wall began to crack in the late 1970s, not from a single dramatic discovery, but from a slow accumulation of data that refused to fit the expected picture. The problem was dimensionality. Every sky survey conducted up to that point had been essentially flat. Astronomers could plot the positions of galaxies on the two-dimensional dome of the sky, assigning each one a right ascension and a declination, the celestial equivalents of longitude and latitude. But the sky is a projection, a shadow cast by a three-dimensional universe onto a two-dimensional surface. Two galaxies sitting side by side in a photograph might be separated by hundreds of millions of light-years in real space, one relatively nearby and the other vastly more distant, compressed together by the act of projection into apparent neighbors. Without the third dimension, without depth, the maps astronomers were building were profoundly misleading. The solution was redshift. As the universe expands, it stretches the fabric of space, and light traveling through that expanding fabric gets stretched along with it. Its wavelength lengthens, shifting toward the red end of the spectrum. The degree of this redshift encodes the distance the light has traveled, and therefore the distance of the galaxy that emitted it. By measuring the precise redshift of each galaxy in a survey, astronomers could add the third dimension to their maps. They could transform a flat projection into a genuine three-dimensional atlas of the cosmos. The instrument work required was painstaking. Spectrographs had to be built capable of splitting the faint light of distant galaxies into their component wavelengths. Observing time had to be secured months, and then years of telescope hours devoted to building statistically meaningful samples. Data reduction was performed largely by hand. In the earliest surveys, each spectrum analyzed individually, each redshift extracted from careful measurements of spectral absorption lines. It was slow, expensive, and enormously labor-intensive, and it produced results that nobody was prepared for. In 1978, Stephen Gregory and Laird Thompson published the results of their redshift survey of the region around the Coma Galaxy Cluster, one of the nearest rich clusters of galaxies to our own position. They had measured the distances to hundreds of galaxies, spread across a wedge of sky, allowing them to plot their true three-dimensional positions for the first time. The distribution they found was nothing like the smooth scattering the cosmological principle predicted. Galaxies clustered together in elongated chains, and concentrated at certain distances while leaving enormous volumes between them almost entirely empty. The smoothness that everyone had assumed was simply not there. The universe seen in 3 dimensions for the first time had texture, structure, gaps, almost simultaneously working from the Tartu Observatory in Estonia. Astronomers Jan Einasto and Marit Jovier arrived at strikingly similar conclusions from a different region of sky. In their 1978 analysis, they described a cosmos organized into cells with galaxies concentrated along the walls of enormous hollow regions. The cells they mapped were not small irregularities. They were vast structured bubbles, each one enclosing a volume of space that contained far less matter than it should. The underdense interiors were surrounded by the thin, luminous skins of galaxy concentrations, and everywhere they looked, the same pattern repeated. The word they used in their papers was cellular. The universe had a cellular structure, and the cells were mostly empty. The resistance from the wider community was immediate. The cosmological principle was not an observation. It was a theoretical prior, a belief about how the universe ought to behave, supported by what now appeared to be insufficiently deep surveys. The redshift surveys of Gregory Thompson, Einasto, and Jovier were probing real 3-dimensional structure for the first time, and what they found was not what the prevailing models predicted. Some cosmologists argued the surveys were too small, too limited in volume to be representative. Others suggested the apparent structure was a statistical artifact, a chance arrangement of galaxies that would wash out into smoothness if the survey were extended further. The extension came rapidly. Throughout the early 1980s, larger and deeper redshift surveys were completed, each one probing a greater volume of the cosmos. And each one found the same thing. Galaxies were not scattered uniformly through space. They formed a network, a web of elongated filaments and broad sheets, enclosing enormous dark interiors. The structure did not wash out with increasing survey depth. It became more prominent, more organized, more clearly real. The definitive early demonstration came in 1981 from a survey of galaxies in the constellation Boötes. Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman had been mapping galaxy positions across a large region of sky when they encountered something that stopped them. In a volume of space, approximately 330 million light-years in diameter, a region large enough to contain several thousand galaxies. Based on the average density measured elsewhere, they found fewer than 60 galaxies, where thousands should have been. The deficit was not ambiguous. It was not a calibration issue or a gap in survey coverage. The Boötes void was real, confirmed by multiple independent observations, a sphere of cosmic space from which galaxies were almost entirely absent. If you stood in the middle of the Boötes void and looked outward in any direction, the nearest substantial galaxy would lie so far away that even our most powerful telescopes would struggle to detect it. The night sky, stripped of almost everything, would be a darkness so complete it would feel less like an observation and more like an erasure. The Boötes void forced cosmologists to take cosmic emptiness seriously for the first time, not as background scenery, not as the unremarkable space between objects of interest, but as a genuine feature of the universe, a structure in its own right requiring explanation within the framework of structure formation theory. And the theory, it turned out, was strained. Producing a void 330 million light-years across through the standard process of gravitational amplification of small primordial fluctuations pushed the models to their limits. The fluctuations seeded during the Big Bang were extraordinarily small variations of roughly 1 part in 100,000 from the average density. Gravity had amplified them over billions of years into the structures observed today. But generating a hole as large as Boötes required the initial conditions to have been unusually smooth over an enormous volume. Possible, but uncommon, a statistical outlier sitting at the edge of what the standard model comfortably predicted. Some cosmologists were relieved by this framing. An outlier was not a contradiction. The universe could produce rare events without breaking any fundamental rules. The Boötes void was simply a roll of the cosmic dice that came up unusual, improbable but not impossible. What none of them yet knew was that Boötes was not the outlier. It was the introduction. The surveys continued. The maps deepened. Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics produced in the late 1980s one of the most famous images in the history of astronomy, a slice through the nearby universe showing thousands of galaxies plotted in their true three-dimensional positions. The image resembled nothing so much as a cross-section of a sponge. Bright concentrations of galaxies traced thin, curved arcs, enclosing dark interior bubbles. The voids were not small, they were not incidental. They were the dominant visual feature of the map, the primary impression the data made on any eye that saw it. The universe was not full. It never had been. The fullness had been an illusion born of flat maps and limited data, and the natural human tendency to see what the prevailing theory predicted. The three-dimensional cosmos was something else entirely. It was a foam, an intricate lattice of matter, stretched across the surfaces of enormous hollow bubbles, each bubble a void, each void expanding outward into the surrounding web, each expansion making the void larger and the surrounding matter denser, and the contrast between empty and full sharper with every passing billion years. The cosmic web had been discovered, and the web, as its most fundamental property, was mostly holes. Understanding what a cosmic void actually is requires dismantling an image that forms almost automatically in the mind the moment the word is spoken. When you hear void, you picture nothing. A true absence. A region of space scrubbed clean of matter, swept bare of every atom, every particle, every photon. The kind of emptiness that exists between the electrons and the nucleus of an atom scaled up to cosmic proportions. A hole in the most literal and absolute sense of that word. That image is wrong. And the way it is wrong matters enormously, because the reality is both more subtle and more consequential than simple emptiness would be. A cosmic void is not a region from which matter has been removed. It is a region where matter never adequately gathered. The distinction sounds semantic until you examine the physics, at which point it becomes the entire story. The universe has an average density, a number calculated by taking the total amount of matter, ordinary atoms, dark matter, diffuse gas, and distributing it uniformly across the total volume of observable space. This average is thin. The cosmos is not, even in its densest regions, anything resembling crowded in the way that word applies to human experience. Matter is sparse everywhere. But there are regions where the local density exceeds the average by large factors, and regions where it falls below. Dense regions, the filaments and walls and clusters of the cosmic web, can exceed the average density by hundreds or even thousands of times. Voids fall below it, typically containing only 10 to 20% of the matter found in a comparable volume of average cosmic space. This means voids are not empty. They contain galaxies, scattered, sparse, separated by distances that dwarf anything in denser regions but present. Stars burn inside those galaxies. Gas drifts through the intergalactic spaces within the void in wisps, too diffuse to collapse into anything new, too thin to register on any instrument, pointed casually in that direction. Dark matter permeates the entire volume, forming a ghostly, invisible scaffolding that connects weakly to the denser structures beyond the void's boundaries. The void is not a true vacuum, it is an underdensity, a place where the cosmic ledger falls short by 15 or 20 or 30%, and that shortfall, invisible on any single observation, has consequences that cascade across billions of light years and billions of years. The consequences begin with gravity. Gravity is at its most fundamental level a relationship between mass and the curvature of space-time. More mass means more curvature, means stronger gravitational attraction. In the dense regions of the cosmic web, gravity is powerful. It draws matter together. It resists the expansion of space. It builds structure, accumulating mass in the nodes and filaments of the web, pulling galaxies into clusters, merging smaller structures into larger ones over cosmic time. In these regions, gravity is winning its contest against the expansion of the universe. Clusters of galaxies are gravitationally bound. They are not being carried apart by cosmic expansion. They hold together because the gravitational attraction between their member galaxies exceeds the outward push of dark energy across the relatively modest distances involved. Inside a void, This contest has a different outcome. The mass is sparse. The gravitational attraction across the void's enormous interior is feeble compared to the scale of the region. And the dominant force in this weakened gravitational environment is dark energy, the mysterious pressure that drives the accelerating expansion of the universe. Dark energy does not clump. It does not concentrate in particular regions or thin out in others. It pervades all of space uniformly, exerting the same outward pressure per unit volume everywhere in the cosmos. In dense regions, gravity is strong enough to overwhelm it, holding structures together and preventing the local expansion of space from pulling them apart. In voids where gravity offers almost no resistance, dark energy controls the dynamics almost entirely without opposition. When dark energy wins, space expands, and inside a void, space expands faster than the cosmic average. This creates a feedback mechanism of remarkable efficiency. As the void expands, the volume it occupies grows larger, while the matter within it remains approximately constant. A larger volume containing the same amount of matter means lower density. Lower density means even weaker gravity. Even weaker gravity means even less resistance to dark energy. The void expands faster, becomes emptier, and accelerates its own growth in a self-reinforcing cycle that has no natural break. The void is not static. It is an engine converting the slight initial underdensity it began with into a growing, deepening, accelerating emptiness that will not stop until the matter surrounding it has been swept away entirely. Meanwhile, the matter that once occupied the region of the forming void does not disappear. It has to go somewhere. Gravity continues to operate at the boundaries between the expanding void and the surrounding cosmic structure. The sparse galaxies within the void feel a net gravitational pull directed outward, toward the denser regions beyond the void's edges. This is not because the void is pushing them. Gravity does not push. It is because all the matter, all the gravitational attraction that these galaxies feel, comes from outside the void. The filaments and walls and clusters of the cosmic web lie beyond the void's boundaries. The interior of the void contains too little mass to generate meaningful gravitational pull. So the net force on every galaxy inside the void points outward toward the edges, toward the matter that dominates in every direction beyond the void's horizon. The result is an outflow. Galaxies drift away from the void's center, accelerating gently outward, decade by decade, and century by century, and eon by eon, until they pile up against the boundaries of the void, adding their mass to the walls and filaments that define the void's outer edge. The void sheds matter like a storm sheds water, driving it outward into the surrounding structure. The edges of the void grow slightly denser as this expelled matter accumulates. The interior grows slightly emptier as the outflow continues. The contrast sharpens, the boundaries become more defined. What began as a modest underdensity in the early universe gradually transforms over billions of years of this patient amplification into the dramatic hollow cavities that appear in modern galaxy surveys. This process, the simultaneous growth of overdense structures and the deepening of underdense voids, is not two separate phenomena. It is one phenomenon seen from two different perspectives. The formation of galaxy clusters and the formation of cosmic voids are the same gravitational story told from opposite ends. Every filament that builds itself up by drawing matter inward creates a void in the region it drains. Every void that expands outward pushes matter into the surrounding web, feeding the growth of the filaments that contain it. The cosmic web and the cosmic voids are not independent structures. They are complementary expressions of the same underlying process, gravitational instability, amplifying the quantum fluctuations of the earliest moments of the universe into the grandest architecture nature has ever produced. The cosmic web itself has four components, and understanding their relationship reveals why voids are not merely the leftover spaces between interesting objects, but the defining feature of the entire structure. The first component is the nodes. These are the densest regions in the observable universe, the intersections where multiple filaments converge. Galaxy clusters form at these crossroads, packing hundreds or thousands of individual galaxies into compact volumes spanning just a few million light-years. The nodes are the brightest, busiest, most dramatic environments in the cosmos. galaxies collide and merge within them. Superheated gas fills the spaces between galaxies at temperatures of hundreds of millions of degrees, glowing in X-rays bright enough to detect across billions of light-years. Supermassive black holes at the centers of cluster galaxies swallow infalling matter and drive enormous jets of energy outward through the surrounding gas. The nodes are where the most extreme versions of nearly every astrophysical process occur. The second component is the filaments. These are the threads that connect the nodes, elongated chains of galaxy groups, and diffuse gas stretching for hundreds of millions of light-years between the cluster intersections. Filaments are the highways of the cosmic web, channeling matter from lower density regions toward the dense nodes at their endpoints, continuously feeding the growth of the most massive structures in the universe. A single filament may contain dozens of galaxy groups, each one a small cluster of a few dozen galaxies strung along its length like beads on a wire. The gas within filaments is warmer and denser than the void interior, but cooler and more diffuse than the hot plasma within clusters, occupying an intermediate environment that astronomers call the warm-hot intergalactic medium. The third component is the walls, sometimes called sheets. These are broad, flat concentrations of galaxies that form where multiple filaments intersect along extended two-dimensional surfaces. Walls are thinner than filaments and less concentrated than nodes, but they cover enormous areas, sometimes stretching for more than 1 billion light-years in extent, while remaining only tens of millions of light-years thick. The Sloan Great Wall, identified in galaxy survey data in 2003, extends approximately 1.4 billion light-years in length, making it one of the largest single structures ever catalogued. Though whether it constitutes a gravitationally bound entity or merely a chance alignment of smaller structures along a line of sight remains a subject of debate. And then there is the fourth component, the one that does not appear in astronomical photographs. The one that generates no light, produces no signal that passive instruments can detect, and leaves no obvious imprint on any image of the sky. The voids. They are not the fourth component in the sense of being fourth in importance or fourth in spatial dominance. They are the fourth component in the sense of being the last to be recognized, the hardest to observe, and the easiest to overlook. But in every physical sense that matters, they are the dominant feature of the cosmic web, not fourth. First, the numbers establish this without ambiguity. Modern galaxy surveys, combined with detailed computer simulations of cosmic structure formation, have converged on a measurement that should permanently change how you imagine the universe. Voids occupy approximately 80 to 90% of the total volume of the observable cosmos. The filaments, walls, nodes, and everything they contain, every galaxy, every star, every planet, every atom of matter that has ever participated in the story of cosmic structure, all of it is packed into the remaining 10 to 20%. The universe is not a sea of galaxies with gaps between them. It is a vast expanse of empty space, with thin threads of matter woven sparsely through it. Pause with that for a moment. Not to let the number sink in, because numbers do not sink in. Let instead an image form. Imagine you could shrink the observable universe to the size of a room, roughly 10 meters on each side. Every galaxy that has ever been observed, every filament and cluster and supercluster that has ever been mapped would occupy a volume roughly equivalent to the walls, floor, and ceiling of that room, not the interior. The surfaces, the thin membrane, everything else, the overwhelming majority of the space inside that room would be void. You could walk to the center of that imaginary room and look in every direction and see nothing but the faint, distant walls of matter at the edges. That is the universe. Not the walls, the room. The walls are the exception. A related comparison makes the point from a different angle. If you could choose a location in the observable universe at random, with perfect mathematical randomness and no bias toward any particular region, the probability that you would land in a void would be between 80 and 90%. The probability that you would find yourself near a galaxy, near a filament, near any structure we would recognize as dense or interesting is somewhere between 10 and 20%. The places we have spent centuries studying, the places our telescopes are designed to find and our cameras designed to photograph, the places where all the interesting physics and all the visible matter and all the known examples of life reside, are the minority, the statistical outlier, the unusual corner. The void is the rule. This inversion has not been absorbed into popular consciousness, and even within the scientific community, it tends to be stated as a fact and then immediately set aside in favor of studying the structures that occupy the minority. Volume. The voids are harder to observe. They do not emit light. They do not produce the signals that astronomical instruments were designed to detect. They announce themselves only as an absence, a region where galaxies fail to appear, and cataloging an absence requires a statistical framework rather than a straightforward detection. You cannot point a telescope at a void and see it. You can only measure the deficit of galaxies and infer from that deficit the presence of underdense space. The statistical tools developed to do this are sophisticated and continue to improve. Scientists divide surveyed volumes into cells, count the galaxies in each cell, compare those counts to the expected average, and identify contiguous regions where the count falls persistently below the mean. Various algorithms have been developed to formalize this process, each defining void boundaries according to slightly different criteria. The Zobov algorithm identifies voids as the union of density basins regions that drain toward a local minimum in the density field. The Void pipeline builds on this approach and produces catalogs of voids with well-characterized properties. Other methods use the shapes of the velocity field, identifying voids by the outflows they drive rather than the galaxy deficits they contain. Each method produces slightly different results in detail, but all of them agree on the broad picture. Voids are everywhere. They span a wide range of sizes from small voids 30 to 50 million light-years across, scattered through the spaces between neighboring galaxy groups, to medium voids of 1 to 300 million light-years that form the PUT, characteristic bubbles of the cosmic foam, to the rare supervoids that exceed 500 million light-years in diameter and strain the standard models of structure formation to produce. The distribution of void sizes follows a pattern. Small voids are common, large voids are rare, and the largest voids of all sit so far out on the probability distribution that their existence challenges the theoretical framework within which cosmologists have been working for decades. The reason supervoids are theoretically challenging returns to the origin of all cosmic structure in the quantum fluctuations of the earliest universe. Those fluctuations were extraordinarily small, 1 part in 100,000 from the mean. Gravity amplified them over billions of years, but it amplified them from an almost perfectly smooth starting point. Producing a void 500 million light-years across requires an initial underdensity spread smoothly over an enormous volume, a starting condition that the statistics of quantum fluctuations predict should occur only rarely. The standard cosmological model lambda-cold dark matter reproduces the observed population of small and medium voids with impressive accuracy. But when researchers search their simulations for supervoids matching the largest examples found in real surveys, they find very few matches. The simulations simply do not produce structures that extreme very often. This discrepancy is one of the active tensions between observation and theory in modern cosmology. It is not a crisis in the way the Hubble tension is a crisis, not yet, but it is a persistent signal that something about the standard picture may be incomplete. Either the initial conditions of the universe allowed for more extreme underdensities than the standard model predicts, or the process of structure amplification is more vigorous than the model's capture, or the observations contain systematic biases that overestimate the sizes and depths of the largest voids. Distinguishing between these possibilities requires more data, deeper surveys, more precise void catalogs, and more sophisticated simulations. The technology to gather that data is arriving. The Euclid Space Telescope, launched in 2023, will map the three-dimensional positions of hundreds of millions of galaxies across billions of light-years, producing the most detailed atlas of the cosmic web ever. Assembled. The Vera C. Rubin Observatory in Chile, beginning its legacy survey of space and time in the mid-2020s, will photograph the entire accessible southern sky every few nights for a decade, building a time-lapse movie of the universe at a depth and breadth never before achieved. Both missions will produce void catalogues of unprecedented size and precision, and both will put the theoretical models under pressure they have never previously faced. But even now, with the data already in hand, there is one void that stands apart from all others, not because it is the emptiest, though it is among the deepest measured, not because it is the most precisely characterized, though multiple independent surveys have confirmed its properties, but because of where it is. Because of the fact that every telescope ever pointed at the sky has been pointed from inside it. Because the universe we think we understand, the one whose expansion rate we have measured, and whose age we have calculated, and whose composition we have mapped with extraordinary precision, has been observed from a position that is not typical. It has been observed from the interior of the largest confirmed cosmic void in the observable universe, and the measurements we have made from inside that void may not mean what we have assumed they mean. 0920, Claude responded. In 2013, 3 astronomers at the University of Hawaii published a paper that did not make headlines in the mainstream press. In 2013, 3 astronomers at the University of Hawaii published a paper that did not make headlines in the mainstream press. It appeared in the Astrophysical Journal, a technical publication read primarily by specialists, and its title was dry enough to deflect casual attention entirely. The authors were Ryan Keenan, Amy Barger, and Lennox Cowie, and what they had found buried inside careful statistical analysis of multiple galaxy catalogues spanning years of accumulated survey data was something that should have stopped the world. They had found us. Not us in the sense of discovering Earth, or the solar system, or the Milky Way. Those had been found long ago. They had found our position in the larger structure of the cosmos, and what they discovered about that position was this: we are not where we thought we were. Not geographically, not in the sense of coordinates or distances, but in terms of what surrounds us, in terms of the cosmic environment we inhabit, in terms of whether the space extending outward from our location in every direction is typical or exceptional. We had been wrong. Profoundly, consequentially, measurably wrong. Keenan, Barger, and Cowie were not initially searching for a void. They were studying something more straightforward, or so it appeared at the outset. They wanted to know how galaxy number density, the count of galaxies per unit volume of space, varied as a function of distance from Earth. It was a diagnostic measurement, the kind of careful calibration work that undergirds the more ambitious projects in observational cosmology. You need to know how galaxies are distributed around you before you can reliably use those galaxies as traces of cosmic structure. The project sounded methodical, procedural. It was exactly the kind of work that tends to generate important discoveries, precisely because the people doing it are paying careful attention to the data rather than to a preconceived result. Their approach was deliberately conservative. They compiled data from several major independent galaxy catalogues, spanning different wavelength bands and using different observational techniques. Some surveys estimated galaxy distances photometrically, using the colors of galaxies as proxies for their redshifts, a technique that trades precision for efficiency, allowing large numbers of galaxies to be processed quickly. Others use spectroscopic measurements, splitting each galaxy's light into its component wavelengths and measuring the precise displacement of known spectral features, a slower and more expensive approach that yields distances accurate to within a fraction of a percent. By combining both types of data across multiple independent surveys, Keenan and his colleagues could test whether any pattern they found was robust, or whether it was an artifact of a single instrument, a single technique, or a single survey's particular biases. What they found was robust. Uncomfortably, persistently, reproducibly robust. In every direction they examined out to distances of approximately 1 billion light-years from Earth, the number density of galaxies fell below the expected cosmic average. Not by a trivial margin, not by a few percent that might be explained by survey incompleteness or calibration uncertainty. The deficit was roughly 20%, everywhere, in every survey, in every wavelength band, in both photometric and spectroscopic data. 1 in every 5 galaxies that should have existed in the volume of space surrounding us based on the average density of matter measured at greater distances and across the broader observable universe was simply absent. The pattern formed a sphere, a colossal underdense bubble centered approximately on our position in the cosmos, extending outward for roughly 1 billion light-years in radius. The full diameter of this structure, the distance from one side to the other, passing through our location, measured approximately 2 billion light-years. The team named it after themselves, the KBC Void. It was the largest confirmed cosmic void ever observed. 2 billion light-years. The number exists on the page and the eye passes over it, and nothing happens, because nothing can happen. The human nervous system did not evolve to respond to numbers of that magnitude. There is no felt sense of 2 billion light-years, no visceral impression of what it means to be separated from something by that distance. The number is formally registered and immediately filed away as large, alongside all the other large numbers that accumulate in any discussion of the cosmos, and the conversation continues as if comprehension has occurred. It has not occurred, so let us try to produce it. Light travels at approximately 1860000 miles per second. In a single year, a beam of light covers roughly 6 trillion miles. That annual distance is 1 light-year, the basic unit of cosmic measurement. 2 billion light-years is 2 billion of those annual distances stacked end to end. It is 12 sextillion miles. Written numerically, that figure requires 22 digits, the number 12 followed by 21 zeros. That is the diameter of the void you are sitting inside. But the number still does not land, so approach it differently. The Milky Way, your home galaxy, measures approximately 100,000 light-years across. It is a large spiral galaxy containing somewhere between 200 and 400 billion individual stars, along with enormous quantities of gas and dust and dark matter. It takes light 100,000 years to travel from one edge to the other, a duration that encompasses the entire history of anatomically modern human beings on Earth, plus several times that span again. The Milky Way is by any standard accessible to human experience, a structure of almost incomprehensible size. To span the diameter of the KBC Void by laying Milky Way galaxies end to end, you would need 20,000 of them, not 20,000 stars. 20,000 entire galaxies, each containing hundreds of billions of stars placed edge to edge in a line stretching from one side of the void to the other. 20,000 galaxies wide. That is the emptiness surrounding us. Try it from another direction. The Andromeda Galaxy is the farthest object visible to the naked human eye. On a clear autumn night, far from city lights, it appears as a faint oval smudge in the constellation Andromeda, a ghostly presence that requires dark adapted eyes and a moment of patience to perceive. It sits approximately 2.5 million light-years from the Milky Way. That distance, 2.5 million light-years, is considered one of the great chasms of the local cosmos. It is the nearest large galaxy to our own, and the light reaching your eyes from it tonight left its source before our species existed. You could fit approximately 800 of those chasms, 800 trips from the Milky Way to Andromeda, laid consecutively end to end inside the diameter of the KBC Void. 800 Andromeda distances. And almost none of that distance, almost nothing along any of those 800 consecutive trips would contain the expected density of matter. Or consider travel time. The fastest spacecraft humanity has ever launched is Voyager 1, which left Earth in 1977 and has been traveling outward through the solar system ever since. As of the early 2020s, Voyager 1 has covered approximately 23 billion kilometers a distance. That sounds enormous until you convert it. 23 billion kilometers is roughly 0.0025 light-years. In nearly 5 decades of continuous travel at speeds, no human spacecraft has surpassed. Voyager 1 has covered 1/400th of 1 light-year. At that rate, crossing the diameter of the KBC Void would require approximately 320 trillion years. For context, the current age of the universe is 13.8 billion years. Voyager 1, traveling at its current speed without stopping or slowing, would need to travel for more than 20,000 times the current age of the universe to cross the void we are sitting inside. These comparisons do not produce comprehension. They produce a kind of structured vertigo, a recognition that the scales involved exceed the mind's capacity for genuine spatial intuition, but that recognition is itself valuable. It marks the boundary of the human imagination and places the void correctly on the far side of it, in the territory of things that can be measured and described, but not truly felt. The discovery of the KBC void raised an immediate question that goes to the heart of observational astronomy. If this structure is so large, why did it take until 2013 to find it? The Boötes void was discovered in 1981. Redshift surveys had been mapping the three-dimensional distribution of galaxies for decades before Keenan and his colleagues published their paper. The cosmic web had been charted in progressively greater detail through the 2-degree field galaxy redshift survey and the Sloan Digital Sky survey. How does a structure 2 billion light-years across hide in plain sight for 30 years? The answer is one of the most fundamental challenges in observational science. We are inside it. Detecting a structure from within it is an entirely different problem from detecting it from outside. If the KBC void were a distant feature of the cosmic landscape, a bubble of underdensity located somewhere across the sky, at a well-defined distance from our position, it would have been straightforward to identify. Astronomers would have pointed their surveys at that region, measured the galaxy density within the bubble, compared it to the surrounding average, and reported the deficit. The detection logic would have been the same as for the Boötes void, just applied to a larger region. But the KBC void is not across the sky. It is all around us. It extends in every direction simultaneously, and its boundary lies not in some particular constellation, but at a radial distance of approximately 1 billion light-years from our position. A sphere surrounding us, rather than a region, we can point toward. To detect a structure you are embedded within, you need a reference point. You need to know what the average density of the universe looks like from outside your local environment, so that you can compare your local measurements to it and identify the discrepancy. For most of the history of observational cosmology, that reference point did not exist with sufficient precision. Early surveys measured galaxy densities within relatively modest volumes, hundreds of millions of light-years at most, and found reasonable agreement with the cosmological principle. The universe appeared roughly uniform at those scales. What they were actually seeing without knowing it was the interior of the void, where the density is relatively consistent because the underdensity is spread uniformly across the entire volume. The smoothness they observed was real, but it was the smoothness of the whole, not the smoothness of a universe without holes. Only when surveys grew deep enough to probe distances well beyond the void's boundaries, to sample the cosmic density at distances greater than 1 billion light-years, could astronomers establish the external reference point needed to recognize the local deficit. Keenan Barger and Cowie succeeded where earlier surveys had not, because they combined data reaching to distances of several billion light-years far beyond the void's edge, giving them a reliable measurement of the true cosmic average against which to compare the local galaxy counts. When they made that comparison, the deficit was unmistakable. 1 in 5 galaxies missing in every direction out to 1 billion light-years. The analogy to perception is precise and instructive. Imagine you were born inside a vast room painted entirely in a shade of blue that is 10% less saturated than the standard blue used in every other room in the building. If you spent your entire life inside that room, you would have no way of knowing the color was unusual. It would simply be the color of the room, the color of your experience, the visual background against which everything else was measured. Only if you stepped outside the room, walked down the corridor, and compared your room's blue to the blue of every other room would the deficit become apparent. The difference would be subtle but real and consistent and impossible to dismiss once seen. Keenan and his colleagues were the first to walk far enough down the corridor. Multiple independent analyses have since confirmed their finding. Research teams using different galaxy catalogs, different survey methodologies, different statistical approaches, and different portions of the sky have all arrived at the same basic result. The local universe, out to approximately 1 billion light-years in every direction from our position, is underdense by roughly 15 to 25%. The exact figure varies somewhat depending on the method used and the specific surveys analyzed. Some analyses find a deficit closer to 15% at the void's center, deepening toward 25% near the transition zone between the void interior and the denser surrounding web. Others measure a more uniform 20% across the full volume. The details are still being refined as new surveys add depth and precision to the available data. But the central finding is no longer in doubt. We live inside a very large hole in the distribution of cosmic matter. What exists within this hole is worth pausing to describe because the KBC void is not empty in the way the Boötes void approaches emptiness. The Boötes void, with its 60 galaxies where thousands should be, approximates genuine desolation. It is a pocket of the cosmos stripped down to almost nothing, a region where, if you lived in one of the rare surviving galaxies, you would look outward in every direction and see almost no neighbors. The KBC void is different in character. It contains real structure, impressive structure that by any ordinary measure would be described as complex and interesting and densely populated. Our own galaxy, the Milky Way, is part of the local group, a collection of roughly 80 galaxies, including the large and small Magellanic Clouds, the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies orbiting the two largest members. The local group spans approximately 10 million light-years and constitutes a gravitationally bound system, meaning its members are not being carried apart by cosmic expansion, but are held together by their mutual gravitational attraction. The local group is itself embedded within the Virgo supercluster, a broader concentration of galaxy groups and clusters, extending across approximately 100 million light-years, and the Virgo supercluster is in turn one component of an even larger gravitational structure called Laniakea. Laniakea, whose name means immeasurable heaven in Hawaiian, was identified in 2014 by Brent Tully and his colleagues using measurements of galaxy peculiar velocities across an enormous volume of the nearby universe. It spans approximately 520 million light-years and contains roughly 100,000 galaxies, with a combined mass of approximately 100 million billion solar masses. Galaxies within Laniakea are not merely nearby in space. They are gravitationally connected, flowing together toward a common attractor, a massive concentration of matter called the Great Attractor, located in the direction of the constellation Centaurus. Laniakea is a gravitational basin, a watershed in the landscape of cosmic mass distribution, and the Milky Way sits near its outer edge. Laniakea, with all its 100,000 galaxies, its thousands of galaxy groups, its dozens of major clusters, its 520 million light-years of gravitationally linked structure, fits inside the KBC void. Not barely. The void is roughly 4 times wider than Laniakea in diameter. You could place several Laniakea-sized superclusters side by side within the void's volume, and the region would still register as underdense compared to the cosmic average. This is the aspect of the KBC void that is most difficult to absorb. It does not feel empty from inside. It contains a supercluster. It contains 100,000 galaxies. It contains the gravitational infrastructure of 500 million light-years of organized cosmic structure, and yet measured against the cosmic average, against what the same volume of space elsewhere in the universe would contain, all of that impressive architecture falls short. The matter is there. The galaxies exist, the stars burn, and the gas flows, and the dark matter halos extend their invisible influence across millions of light-years. But the ledger does not balance. 1 in 5 of the entries that should appear on that ledger is missing. The deficit matters not as an abstract accounting discrepancy, but as a physical reality, with consequences that cascade through every measurement made from within the void. A 20% shortfall in matter density translates directly to a 20% shortfall in gravitational pull. Less gravitational pull means less resistance to the expansion of space. Less resistance means local space expands slightly faster than the cosmic average. Faster expansion means galaxies inside the void appear to recede from us more quickly than they would if the void did not exist. Faster apparent recession means higher measured redshifts. Higher measured redshifts, when interpreted without accounting for the void's outflow, produce a falsely elevated estimate of the universe's expansion rate. The void is not merely a fact about where we live. It is an active distortion in every telescope observation ever made from the surface of the Earth or from any satellite orbiting within the void's boundaries. It inflates the velocities we measure. It biases the distances we infer. It systematically skews the most precisely measured number in all of cosmology. And for decades, we measured that number without knowing the void was there. The most precisely measured number in the history of cosmology is also the most contested. It is called the Hubble constant, and it describes something deceptively simple: how fast the universe is expanding. For every megaparsec of distance between 2 points in space, roughly 3.26 million light-years, the universe stretches by a certain number of kilometers per second. Measure that number accurately and you hold in your hands the heartbeat of the cosmos. From it flows the age of the universe, the density of dark energy, the curvature of space-time, the ratio of matter to radiation, the ultimate fate of everything that exists. Nearly every calculation in modern cosmology connects back to this single quantity. It is not one measurement among many, it is the foundation. For decades, measuring it accurately was considered one of the great unsolved problems in observational astronomy. Early estimates by Edwin Hubble himself, published in 1929, suggested a value of approximately 500 kilometers per second per megaparsec, a number so high it implied a universe younger than the Earth itself, a contradiction that would take decades of careful revision to resolve. By the 1970s and 1980s, two camps of astronomers had formed, one centered around Alan Sandage, arguing for a value near 50, the other led by Gérard de Vaucouleurs, arguing for a value near 100, and the disagreement was bitter enough to divide the field for a generation. The dispute was not merely technical, it was personal, entrenched, and resistant to resolution because the underlying measurements were genuinely difficult and the systematic errors genuinely large. The breakthrough came with the Hubble Space Telescope, launched in 1990, specifically to resolve this controversy, among other goals. By observing Cepheid variable stars, stars that pulsate with a period precisely related to their intrinsic luminosity in galaxies at known distances, the Hubble Key Project team, led by Wendy Friedman, spent a decade building a calibrated distance ladder that ultimately converged on a value of approximately 72 kilometers per second per megaparsec, published in 2001. The error bars were the smallest ever achieved. The Hubble constant controversy, it seemed, had finally been resolved. It had not been resolved. The controversy had merely gone underground, waiting for the measurements to become precise enough to reveal a deeper problem. That problem emerged over the following 2 decades, as two fundamentally different methods of measuring the Hubble constant produced two fundamentally different answers, each with error bars small enough to make the disagreement statistically undeniable. The first method reaches back to the beginning of time. The cosmic microwave background, the ancient light released 3800,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, encodes detailed information about the conditions in the early cosmos. The temperature fluctuations in this radiation mapping, variations of a few millionths of a degree across the entire sky, reflect the density fluctuations that existed when the universe was less than 1% of its current age. By measuring these fluctuations with extraordinary precision and feeding the data into the standard cosmological model, scientists can calculate what the expansion rate of the universe should be today, extrapolating forward from the early to universe through 13.8 billion years of cosmic evolution. The Planck satellite, a European Space Agency mission that mapped the cosmic microwave background with the highest precision ever achieved, produced its final results in 2018. The Hubble constant inferred from Planck's measurements was 67.4 kilometers per second per megaparsec, with an uncertainty of less than 1%. It was a triumph of precision cosmology, the most accurate determination of this number ever extracted from the early universe. The second method looks at the nearby universe directly. Astronomers observe objects with known intrinsic luminosities, cosmic measuring sticks, that allow distances to be calculated by comparing how bright an object appears against how bright it actually is. Two types of objects serve this purpose with particular reliability. Cepheid variable stars pulsate with periods precisely related to their true luminosity, allowing distances to nearby galaxies to be measured by timing the pulsations and comparing the expected brightness to the observed brightness. Type Ia supernovae, the thermonuclear explosions of white dwarf stars that have accumulated enough mass to exceed a critical threshold, reach approximately the same peak luminosity regardless of where and when they occur, making them visible across billions of light years and providing distance measurements that probe the expansion rate across cosmic history. By calibrating Cepheid distances in nearby galaxies, and then using those calibrated galaxies as anchors for a larger network of Type Ia supernovae stretching across billions of light years, astronomers can measure the local expansion rate directly without assuming any particular cosmological model. The SH0ES collaboration led by Adam Rees of Johns Hopkins University has refined this measurement over more than a decade of dedicated work using Hubble Space Telescope observations and more recently data from the James Webb Space Telescope. Their most recent results converge on a value of approximately 73 kilometers per second per megaparsec, 67 versus 73, a difference of roughly 9%. 9% sounds manageable. In everyday contexts, a 9% discrepancy between two measurements of the same quantity would be unremarkable, well within the range of normal experimental variation. But these are not everyday measurements. They are the most precisely determined values of the Hubble constant ever obtained, each carrying uncertainties of only a few percent. When the error bars on both measurements are taken into account, the disagreement between them reaches a statistical significance of approximately 5 sigma. In the language of statistics, 5 sigma means there is less than a 1 in a million probability that the discrepancy is the result of random chance alone. In particle physics, 5 sigma is the threshold for declaring a new discovery. In cosmology, it signals a genuine crisis. Both measurements are almost certainly correct in the sense that they accurately measure what they are measuring. The Planck value of 67.4 accurately describes the expansion rate inferred from the early universe using the standard cosmological model. The SH0ES value of 73 accurately describes the expansion rate measured locally using Cepheids and supernovae. The problem is not that either measurement is wrong. The problem is that they are not measuring the same thing, and the reason they are not measuring the same thing may be sitting all around us, extending in every direction for 1 billion light years. This is where the KBC void enters the crisis directly. Consider what the local measurement is actually doing. The Cepheid and supernova distance ladder samples galaxies within a volume of space, extending outward from Earth to distances of several hundred million light-years at most for the Cepheid calibrators and several billion light-years for the most distant supernovae. The galaxies at the foundation of this distance ladder, the ones whose Cepheid distances anchor the entire calibration, lie well within the boundaries of the KBC void. The galaxies used to measure the supernovae at moderate distances also lie largely within or near the void. The entire local measurement is in a very real sense a measurement of the expansion rate as experienced from inside an underdense bubble. Inside that bubble, the outflow driven by the void's gravitational imbalance adds velocity to every galaxy. Every galaxy within the KBC void is moving outward from the void's center, accelerated by the net gravitational pull of the denser regions beyond the void's edge. This outflow is not random. It is coherent and systematic, pointing in the same general direction for all galaxies within the void outward. When astronomers measure the redshift of a galaxy inside the void and use that redshift to infer how fast the universe is expanding, they are measuring the true cosmic expansion plus the outflow velocity added on top of it. The two contributions are entangled in the redshift signal, indistinguishable, without knowing in advance that the outflow exists. The magnitude of this effect has been calculated carefully by multiple research groups. A void of the KBC's dimensions and depth 2 billion light-years across, with a 20% underdensity, generates an outflow that boosts the apparent local Hubble constant by approximately 3 to 5 kilometers per second per megaparsec above the true cosmic value. The true value, the one the Planck satellite measures from the early universe, is approximately 67.4. Add 3 to 5 from the void's outflow and you arrive at approximately 70 to 73. The range brackets the SH0ES measurement almost precisely. The match is not perfect. Different analyses of the void's profile produce slightly different estimates of the outflow boost, and the uncertainties in the void's depth and extent introduce additional scatter. Some researchers argue the void can account for only part of the Hubble tension, perhaps 2 or 3 kilometers per second per megaparsec, of the roughly 6 kilometer per second per megaparsec discrepancy, with the remainder requiring additional explanation. Others find that a more careful treatment of the void's full three-dimensional structure, accounting for its irregular shape, and the presence of denser structures like Laniakea within its boundaries, can account for essentially the interior tension. The debate is active and unresolved, but the direction is unambiguous. The void makes the local expansion appear faster. The local measurement exceeds the global measurement. The excess is comparable in magnitude to the discrepancy between the two Hubble constant determinations, and the void is confirmed by multiple independent lines of evidence to exist, to have the dimensions required, and to drive exactly the kind of outflow that would inflate the local measurement in exactly the way observed. This is not a hypothesis assembled after the fact to rescue a failing model. The KBC void was identified through galaxy density measurements that had nothing to do with the Hubble tension. The outflow it drives was predicted by standard gravitational physics before the Hubble tension had reached its current severity. The expected magnitude of the expansion boost was calculated from void properties measured independently of the supernovae used to determine the local Hubble constant. The pieces fit together not because they were designed to fit, but because they were measuring the same underlying physical reality from different angles. The implications of this explanation extend beyond the Hubble constant itself into one of the most fundamental parameters of cosmology, the age of the universe. The age of the cosmos is calculated from the expansion rate. A faster expansion rate means the universe reached its current size more quickly, implying a younger age. A slower expansion rate means it took longer, implying an older age. The Planck value of 67.4 produces an age of approximately 13.8 billion years. If the higher local value of 73 were taken as the true global expansion rate rather than a locally inflated measurement, the implied age of the universe would drop to approximately 12.7 billion years. 12.7 billion years. Hold that number against another. The oldest stars known in the observable universe are found in globular clusters orbiting the Milky Way ancient stellar populations, whose ages can be determined from their chemical compositions and the physics of stellar evolution. The oldest of these stars have ages estimated at approximately 13 to 13.2 billion years, with uncertainties of a few hundred million years. A universe only 12.7 billion years old cannot contain stars that are 13 billion years old. The stars would be older than the universe that produced them, a logical impossibility that would require either the stellar age estimates or the cosmological model, or both, to be fundamentally wrong. This age paradox has shadowed the high local Hubble constant for years, an uncomfortable consequence of taking the local measurement at face value as a description of the global universe. The void hypothesis dissolves it cleanly. If the local Hubble constant is elevated not because the universe truly expands faster than the Planck value implies, but because the outflow of the KBC void has added several kilometers per second per megaparsec to every local velocity measurement, then the true global expansion rate is 67.4, the universe is 13.8 billion years old, and the oldest stars fit comfortably within that timeline. The paradox was an artifact of location all along. The broader significance of this resolution reaches into the cosmological principle itself, that foundational assumption that our position in the universe is not special, that measurements made from Earth reflect universal properties rather than local accidents, has never been seriously tested on the scale of the KBC void. It was assumed to hold because the alternative, that we happen to occupy an unusually underdense region of the cosmos, seemed improbable enough to ignore. But the probability of finding ourselves inside a void of the KBC's dimensions, while genuinely low, is not zero. And if we do happen to occupy such a void, then every local measurement we have ever made has been made from inside a gravitational environment that systematically differs from the cosmic average. The cosmological principle does not say that inhomogeneities cannot exist. It says they should not persist at scales large enough to affect global measurements. The KBC void at 2 billion light-years may be approaching that limit. Whether it crosses it depends on how precisely the void's influence can be characterized and subtracted from local measurements, a calculation that requires better data than is currently available, but that upcoming surveys will provide. There are cosmologists who resist the void explanation for the Hubble tension. Their objections are serious and deserve acknowledgement. The most significant is that the KBC void, while confirmed in galaxy density, has not been independently confirmed through the velocity field with the precision required to definitively attribute the full Hubble tension to its outflow. Bulk flow measurements, the large-scale coherent motions of galaxies driven by the void's gravitational imbalance, do show anomalously high values compared to standard model predictions consistent with the void's influence, but the measurements carry uncertainties large enough to prevent a definitive statement. The void explains the tension. It does not yet prove the explanation is complete. Other proposed solutions to the Hubble tension remain viable. Early dark energy, a hypothetical burst of additional expansion shortly after the Big Bang that would alter the sound horizon distance used to calibrate the Planck measurement, is among the most discussed alternatives. Modifications to the properties of dark matter in the early universe have also been proposed. Self-interacting dark matter, decaying dark matter, and various extensions to the standard model of particle physics have all been invoked as potential contributors. None has achieved consensus, and most face their own tensions with other cosmological observations when examined carefully. The field is genuinely uncertain. The Hubble tension may ultimately require multiple partial explanations, with the void accounting for some portion of the discrepancy and new early universe physics accounting for the remainder. Or it may turn out that the void alone is sufficient, and the apparent need for new physics dissolves once the void's influence is properly subtracted from local measurements. Or the tension may point towards something deeper, a modification of general relativity, or a departure from the standard cosmological model that has not yet been imagined. What is clear is this: the KBC void is real. It surrounds us. It drives an outflow that inflates our local measurement of the expansion rate, and the magnitude of that inflation is comparable to the magnitude of the most significant discrepancy in modern cosmology. Whether the void is the entire explanation part of the explanation, or a contributing factor that interacts with other unknown physics, it cannot be ignored in any serious attempt to resolve the tension. We have been measuring the universe from inside a hole and interpreting the measurements as if we were standing on level ground. The hole is real. The measurements are real. What may not be real, or at least what may not be universal, is the interpretation we have placed on them. The Hubble tension is not merely a disagreement between two numbers. It is a signal that our view of the cosmos has been filtered through an emptiness we did not know was there. And now that we know it is there, the question is no longer whether it affects our measurements. The question is how deeply the distortion runs, and how much of what we believe about the universe must be revised once the void's influence is properly accounted for. The revision, when it comes fully, will not be catastrophic. The universe is still approximately 13.8 billion years old. Dark energy still dominates the energy budget of the cosmos. The Big Bang still happened. General relativity still governs the large-scale behavior of space-time. These foundations are not threatened by the void, they are clarified by it. But the numbers built on those foundations, the precise values of the expansion rate, the exact densities of matter and dark energy, the fine details of the universe's thermal history, all of those numbers carry a systematic uncertainty introduced by our location that previous analyses did not adequately account for. We are in the most literal sense inhabitants of a biased corner of the cosmos, not biased toward density, toward the rich filaments and crowded clusters where most galaxies reside and where most of the interesting physics occurs, biased toward emptiness, toward the quiet, dark, underpopulated interior of a void that spans 2 billion light-years and contains among its sparse and isolated structures the only planet in the known universe from which any of this has ever been measured or understood or wondered about. 0925, Claude responded. Inside the KBC void, scattered across 2 billion light-years of underdense space galaxies, exist in a condition that has no parallel in the denser regions of. Inside the KBC void, scattered across 2 billion light-years of underdense space galaxies, exist in a condition that has no parallel in the denser regions of the cosmic web. They are not merely distant from one another in the way that all galaxies are distant from one another. They are isolated in a deeper sense, separated by intervals so vast that the gravitational conversations that shape galaxy evolution in crowded environments simply cannot occur. The interactions that transform galaxies, that strip their gas and trigger their star formation and warp their shapes and funnel material toward their central black holes, happen rarely here, if they happen at all. The galaxies of the void have grown up largely alone, and alone they have become something different. To understand what that difference means, it helps to understand first what a galaxy's life looks like in the dense regions of the cosmic web, in the filaments and clusters that occupy the luminous minority of cosmic volume. In those environments, galaxies do not exist in isolation. They move through space in the company of hundreds or thousands of neighbors, gravitationally bound into groups and clusters that have been accumulating mass and complexity for billions of years. The distances between neighboring galaxies in a rich cluster can be comparable to the diameters of the galaxies themselves, a degree of crowding that has no analog in everyday experience, but that produces consequences measurable across billions of light years and billions of years of cosmic time. In these crowded environments, galaxies interact constantly. A galaxy moving through a cluster at several hundred kilometers per second passes close to its neighbors repeatedly over cosmic time, and each close passage exerts tidal forces that distort the passing galaxy's shape, warp its spiral arms, and pull streams of gas and stars out of its outer regions into long tidal tails that stretch between the galaxies and eventually disperse into the intergalactic medium. These tidal interactions are violent by astronomical standards, reshaping galaxies over timescales of hundreds of millions of years, stripping them of the loosely bound material in their outer disks and halos, while leaving the denser inner regions more intact. More consequential than tidal stripping is a process called ram pressure stripping. When a galaxy moves through the hot diffuse gas that fills the space between cluster members, a medium called the intracluster medium, heated to temperatures of tens of millions of degrees by the gravitational energy of the cluster assembly, it experiences a headwind. The galaxy's own gas, the cold neutral hydrogen that fills its disk and serves as the raw material for star formation, is pushed backward by this headwind and eventually stripped away, entirely blown out of the galaxy, like leaves stripped from a tree by a violent storm. The stars, bound by gravity and offering very little cross-section to the ram pressure, remain. But the gas, the fuel for future star formation, is gone. The galaxy is left gas-poor and star formation poor, unable to build new stellar populations because the material required for that construction has been removed by the cluster environment. A third mechanism operates more subtly but with equal effectiveness over longer timescales. In dense environments, a galaxy's extended hot gas halo, the reservoir of diffuse warm gas surrounding the galaxy's disk that slowly cools and falls inward to replenish the cold gas consumed by star formation, is disrupted by gravitational interactions and ram pressure. Without this halo, the galaxy cannot replenish its cold gas supply. Star formation does not stop immediately. The galaxy consumes whatever cold gas remains in its disk over hundreds of millions of years, and during this period, it appears relatively normal. But eventually, the reservoir runs dry and star formation ceases entirely. The galaxy fades its young blue stars, dying out without replacements, its color shifting from the blue of active star formation toward the red of an aging stellar population. Astronomers call this process strangulation, and it is among the most common fates of galaxies that fall into massive clusters. Taken together, tidal stripping, ram pressure, stripping, and strangulation constitute an environmental processing system of remarkable efficiency. Galaxies that enter dense clusters as gas-rich spirals with active star formation emerge over billions of years as gas-poor ellipticals, their spiral structure destroyed by mergers, their star formation extinguished by the removal of their fuel supply, their shapes transformed from the flat disks of actively star-forming systems into the smooth, round profiles of galaxies that have exhausted their creative potential. The cluster environment accelerates evolution, pushing galaxies through their life cycles faster than internal processes alone would drive them. Inside the KBC void, none of this operates. The distances between galaxies are too large for tidal interactions to be frequent. The intracluster medium is too thin and too cool to exert meaningful ram pressure on any galaxy moving through the void. The galaxy groups within the void are small and loosely bound, lacking the deep gravitational wells and hot dense gas of massive clusters. Galaxies within the void move through an environment so gentle that the forces shaping them come almost entirely from within rather than without. Internal processes, the self-regulated cycle of star formation and stellar feedback, the slow stirring of spiral density waves, the gradual accretion of gas cooling from the galaxy's own halo govern their evolution without the constant interruption of environmental violence. The result is a population of galaxies that looks fundamentally different from what you find in the nodes and filaments of the cosmic web. Void galaxies tend to be smaller and less massive than their counterparts in dense regions. They are predominantly late-type systems, spirals, and irregular galaxies, rather than the ellipticals that dominate cluster cores. Their morphologies are often strikingly undisturbed. The spiral arms are smooth and symmetric, the disk profiles regular and unwarped, the rotation curves clean and unperturbed by any recent gravitational encounter. These are galaxies that have never been through anything dramatic. They wear their history, or rather their lack of history, in the orderliness of their structure. The most distinctive property of void galaxies is their gas content. Gas is the currency of galactic evolution. Galaxies that are gas-rich are galaxies with a future capable of continued star formation and the ongoing chemical enrichment that transforms pristine primordial hydrogen into the heavier elements required for planets and ultimately for the chemistry of life. Galaxies that are gas-poor are galaxies winding down their star-forming potential, spent their populations aging without renewal. In dense environments, the mechanisms described above drain galaxies of their gas over billions of years of environmental exposure. Void galaxies are protected from all of these mechanisms simultaneously. Observations confirm this protection quantitatively. Surveys of the neutral hydrogen content of void galaxies conducted using radio telescopes sensitive to the 2-1 centimeter emission line of neutral hydrogen atoms consistently find that void galaxies contain proportionally more gas relative to their stellar mass than comparable galaxies in denser environments. Some void galaxies are among the most gas-rich systems known anywhere in the observable universe, harboring enormous reservoirs of neutral hydrogen that have never been compressed into stars, never stripped away by interactions, never heated beyond the collapse threshold by external radiation fields. This gas richness creates a puzzle that illuminates something deep about the triggers of star formation. You might expect that more gas means more star formation. More fuel should mean more burning. But the relationship between gas content and star formation rate in void galaxies breaks this intuition. Despite their enormous gas reservoirs, void galaxies tend to have lower star formation rates per unit of stellar mass than galaxies in denser environments. They are sitting on a fortune in raw material and spending it with extraordinary restraint. The explanation lies in the physics of star formation itself. Gas does not spontaneously collapse into stars. It requires a trigger, a compression event that raises the local density of a gas cloud above the critical threshold for gravitational collapse. In dense environments, those triggers are abundant. Galaxy mergers drive tidal shocks through the interstellar medium, compressing gas clouds across the entire disk simultaneously. Ram pressure creates turbulence at the stripping boundary, triggering bursts of star formation even as it ultimately removes the gas. Tidal interactions distort the disk, creating regions of elevated pressure where gas piles up and collapses. Even the shock waves from nearby supernovae, propagating through the dense interstellar medium of a cluster galaxy, can trigger cascades of star formation in neighboring gas clouds. In voids, these triggers are absent. The gas sits in extended stable reservoirs, undisturbed by interactions, gently rotating in the galaxy's gravitational well, patiently waiting for a compression that rarely arrives. Star formation proceeds at the slow background rate driven by internal mechanisms, primarily the passage of spiral density waves through the disk, gentle enough to trigger modest ongoing star formation without consuming the gas supply. Rapidly, the galaxy evolves, but at a pace so leisurely that it would take far longer than the current age of the universe to process its entire gas reservoir into stars. When star formation does ignite dramatically in a void galaxy, the result can be spectacular precisely because the gas reservoir is so large. Any event capable of compressing a significant fraction of the available gas simultaneously can produce a starburst, a brief, intense episode of star formation consuming more gas per year than the galaxy would normally process in millions of years. Some void galaxies caught in the act of such a starburst exhibit star formation rates comparable to the most actively star-forming galaxies anywhere in the cosmos, suggesting that the enormous untapped gas supply once triggered sustain an extraordinary burst of stellar creation. But these events appear to be driven by internal instabilities rather than external interactions, and they are less common in voids than in dense environments where external triggers are frequent. The chemical composition of void galaxies provides a precise quantitative record of their unhurried evolutionary histories. Stars create heavy elements, everything heavier than helium through nuclear fusion in their cores. When stars die, they distribute these heavy elements into the surrounding gas through stellar winds and supernova explosions. Over successive generations of star formation, the gas in a galaxy becomes progressively enriched with these metals, a process called chemical evolution, whose pace tracks the rate at which stars form and die. A galaxy with a long history of vigorous star formation will have highly enriched gas. A galaxy with a slow, restrained history of star formation will have less enriched, more metal-poor gas. Spectroscopic observations of void galaxies confirm that their gas is systematically less chemically enriched than comparable galaxies in dense environments. They have lower metallicities. Fewer generations of stars have cycled through their interstellar medium. Fewer heavy elements have been forged in stellar cores and returned to the gas reservoir. The chemical clocks of void galaxies run slower, and the readings they provide are consistent with the picture of isolated, unhurried evolution that the other evidence supports. The dark matter halos surrounding void galaxies add another layer to this portrait. Every galaxy inhabits a much larger halo of dark matter, an invisible gravitational scaffold extending far beyond the visible stars and gas. In dense environments, these halos are subject to constant gravitational harassment. Neighboring halos overlap and interpenetrate, exerting tidal forces that distort their shapes and strip material from their outer regions. The halos of cluster galaxies are truncated and distorted their shapes, reflecting the crowded environment as clearly as the shapes of their host galaxies. In voids, halos are largely undisturbed. They grow smoothly from the outside, accreting dark matter from their surroundings without the complications of frequent interactions. They remain more spherical, more extended, and more representative of how dark matter behaves in the absence of environmental complications. This makes void galaxy halos particularly valuable as probes of dark matter physics. Many of the most important questions about dark matter concern the distribution of mass within halos, the density profile from the center outward, the degree to which dark matter concentrates in the innermost regions, the shape of the halo, its outer edges. These properties are predicted in detail by different theoretical models of dark matter, and distinguishing between models requires measuring halo properties in systems where the signal is clean and uncontaminated by environmental effects. Void galaxy halos undisturbed by the tidal stripping and merging that complicates halo measurements in dense regions offer the cleanest available laboratory for testing dark matter theories in the real universe. But the most fundamental laboratory function of cosmic voids extends beyond individual galaxy properties into the nature of the force that governs the large-scale dynamics of the entire cosmos. Dark energy, the mysterious pressure driving the accelerating expansion of the universe, remains one of the deepest unsolved problems in all of physics. Discovered in 1998 through observations of distant Type Ia supernovae by two independent teams, Saul Perlmutter's Supernova Cosmology Project and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, dark energy earned its discoverers the 2011 Nobel Prize in Physics. But the prize recognized the discovery of a phenomenon whose fundamental nature remains entirely unknown. Dark energy constitutes approximately 68% of the total energy content of the observable universe. It exerts a negative pressure on space-time, accelerating the expansion of the cosmos rather than decelerating it as gravity does. Its most mathematically natural form is the cosmological constant, a term originally introduced by Einstein into his equations of general relativity and later abandoned, representing a constant energy density woven uniformly into the fabric of space-time itself. The cosmological constant does not dilute as the universe expands. It does not vary across space or evolve over time. It is simply there everywhere, always at the same density, exerting the same outward pressure per unit volume regardless of location or epoch. The cosmological constant fits the available data remarkably well. The geometry of the cosmic microwave background, the clustering statistics of galaxies across billions of light-years, the distance redshift relationship of thousands of Type Ia supernovae, all of these observations are consistent with a dark energy that has remained approximately constant over the last several billion years. But consistent with is not the same as proven. The uncertainties in current measurements are large enough to accommodate a dark energy that varies slowly over time or differs slightly from one region of space to another. Distinguishing the cosmological constant from these more exotic alternatives is one of the primary scientific goals of the next generation of cosmological surveys. Cosmic voids offer the cleanest possible environment for making these measurements. In dense regions of the cosmic web, the gravitational influence of nearby masses contaminates the signal of dark energy expansion. Separating the contribution of dark energy from the contribution of gravity requires careful modeling of the local mass distribution, introducing systematic uncertainties that are difficult to eliminate. Inside voids where gravity is feeble and dark energy faces almost no opposition, the expansion signal is dominated by dark energy, with minimal gravitational contamination. The dynamics of void interiors are to a greater degree than any other cosmic environment a direct expression of dark energy's properties. Several specific signatures within voids serve as diagnostic tools for dark energy physics. The rate at which voids expand over cosmic time encodes information about how dark energy has evolved. If dark energy is the cosmological constant unchanged over billions of years, voids should have expanded at a predictable rate throughout cosmic history. If dark energy has grown stronger over time, voids should have expanded faster in more recent epochs. If it has weakened, the expansion rate should have slowed. By measuring the sizes of voids at different distances, and therefore at different look-back times in cosmic history, astronomers can trace the evolution of dark energy across billions of years. The shapes of voids provide an independent probe. In a universe where dark energy is truly uniform and where the geometry of spacetime is exactly flat, voids should appear statistically spherical when averaged over many examples. But if the universe has a slight curvature, or if dark energy varies across space, voids will appear systematically elongated or flattened in ways that betray the underlying geometry. The Alcock-Pajinsky test uses exactly this principle, comparing the apparent shapes of voids measured in redshift surveys to the shapes expected in a geometrically flat universe with a cosmological constant. Any deviation from the expected shape constrains alternative dark energy models and measures the universe's geometry with a precision that complements other methods. The KBC void, as the largest and nearest supervoid ever confirmed, occupies a unique position in this experimental program. Its proximity allows measurements at a level of detail impossible for more distant voids. The galaxies within it are bright enough to be observed spectroscopically, with existing instruments yielding precise velocity measurements rather than the photometric estimates required for fainter, more distant systems. The void's large angular size on the sky means that its internal structure can be mapped at high spatial resolution, revealing the density profile from center to edge with a fidelity that smaller or more distant voids cannot provide. Every galaxy within the KBC void is in a sense an instrument. Its position encodes the density field. Its velocity encodes the gravitational dynamics. Its gas content, its star formation rate, its chemical composition, its morphology, all encode the history of its evolution in an environment dominated by dark energy rather than gravity. The void is not merely empty space. It is a laboratory 2 billion light-years across, containing within it the evidence needed to answer some of the most fundamental questions about the force that will ultimately determine the fate of everything. The irony is not lost on anyone who thinks carefully about it. We live in a corner of the universe where matter chose not to concentrate, where the ordinary processes of structure formation, the gravitational amplification of primordial fluctuations that built every galaxy and cluster and filament in the cosmic web, operated with diminished efficiency, where dark energy exerts its influence more completely than anywhere else in our observable corner of the cosmos. We inhabit, without choosing it and without knowing it, for most of human history, the environment best suited to probing the force that will one day consume everything. The universe, in its indifference to the preferences of its inhabitants, placed the only minds capable of studying dark energy precisely where dark energy's effects are most clearly expressed. Whether that is remarkable or merely coincidental depends on how you interpret the silence that follows the observation. The universe has a direction. It is not a direction in space, not a compass bearing or a celestial coordinate. It is a direction in time, an arrow pointing from the structured complexity of the present towards something simpler and darker and emptier. Every measurement cosmologists have made of the large-scale dynamics of the cosmos points the same way. The voids are growing, the filaments are thinning. The cosmic web is losing the contest. It has been fighting against dark energy since the moment the universe began, and the outcome of that contest extended across timescales that dwarf the current age of the cosmos is not in doubt. To understand where the universe is going, it helps to understand precisely what dark energy is doing right now, and why its victory over structure is not immediate but inevitable. At the present cosmic epoch, dark energy and gravity exist in an uneasy coexistence. In the densest regions of the cosmic web, gravity holds the advantage. The gravitational binding energy of a massive galaxy cluster, the energy required to pull all its member galaxies away from one another against their mutual attraction, exceeds the expansive force dark energy exerts across the cluster's relatively modest volume. The Milky Way and Andromeda are gravitationally bound to each other. They are, in fact, approaching each other, drawn together by mutual gravitation across the 2.5 million light-years between them. In approximately 4 to 5 billion years, they will collide and merge into a single, larger galaxy. Dark energy cannot prevent this. The gravitational attraction between them is too strong, and the distance too small for the expansive pressure of dark energy to overcome it. The local group as a whole, our modest collection of roughly 80 galaxies, spanning about 10 million light-years, is gravitationally bound. Its members will remain together. The Virgo cluster, the nearest rich cluster of galaxies containing approximately 1,300 member galaxies spread across about 8 million light-years, is gravitationally bound. The Perseus cluster, the Coma cluster, the Fornax cluster, all of the massive concentrations of galaxies that define the nodes of the nearby cosmic web are gravitationally bound. They will not be torn apart by dark energy on any timescale relevant to the current epoch or even to many epochs that follow. But between these gravitationally bound islands in the spaces where the density of matter is insufficient to generate binding gravitational forces, dark energy is already winning. Galaxy groups at the peripheries of larger structures, loosely associated collections of a few dozen galaxies that are not tightly gravitationally bound, are already being separated by the expansion of space. The members of these groups are drifting apart, their peculiar velocities the motions driven by gravitational attraction toward one another are insufficient to overcome the recession velocity driven by cosmic expansion across the distances involved. Given enough time, these loose associations will dissolve their member galaxies carried apart into isolation by the expansion of the space between them. This process is already measurable. Surveys of galaxy velocity fields show that the rate at which galaxies in loose groups drift apart is consistent with the predictions of a dark energy-dominated universe. The expansion is not aggressive at present. It does not feel violent or dramatic from the perspective of any given galaxy, but it is relentless. It does not pause, it does not weaken, and over the timescales relevant to cosmic evolution, measured in the tens and hundreds of billions of years, rather than the millions and billions of years over which most astronomical processes operate, relentlessness is sufficient. The cosmic web itself is not a permanent fixture. It is a temporary configuration, a stage in the evolution of the universe that exists only because the current epoch happens to fall within the narrow window of cosmic time, when gravitational structure, formation, and dark energy expansion are closely enough matched to produce the elaborate architecture we observe. That window is closing. It has been closing since the moment dark energy began to dominate the universe's energy budget approximately 5 billion years ago. And as it closes, the web will unravel. The unraveling begins at the peripheries in the tenuous connections between structures rather than within the structures themselves. The filaments that thread through the cosmic web are not uniformly dense. They are thicker and denser near the nodes where they terminate, where matter has been accumulating for billions of years, and thinner and more diffuse in their midpoints, where the connection between two distant nodes is maintained by a relatively sparse stream of galaxies and gas. It is these midpoints, these attenuated bridges between distant clusters, that dark energy will sever first. As the voids on either side of a filament expand, they push the filament from both sides, compressing it laterally and stretching it longitudinally. The filament does not break cleanly. It thins its galaxy density, dropping as the voids encroach on its volume. The galaxy groups along its length, no longer fed by the flow of material channeled from surrounding regions, begin to lose the accretion that sustained their growth. They stop growing, they stabilize. And then, as the voids continue to expand and the filament continues to thin the loosely bound groups, at the filament's midpoints begin to drift apart their connection to the broader web, weakening as the expansion of surrounding voids stretches, the distances between them beyond the reach of gravitational attraction. Over timescales of roughly 100 billion years, approximately 7 times the current age of the universe, the majority of filamentary connections in the cosmic web will have dissolved. The nodes will remain the massive clusters that sit at the intersections of multiple filaments, retaining their gravitational cohesion even as the threads connecting them to one another disappear. But the nodes will become islands, isolated, separated from one another by expanding voids whose dimensions will by then dwarf anything in the current universe. The cosmic web will not have been destroyed. It will have been reduced to its most massive and most gravitationally robust components, floating separately in a darkness that no longer connects them. The galaxies within these isolated clusters will not simply stop evolving when their cluster becomes an island. They will continue to interact with one another, governed by the same gravitational dynamics that have shaped their evolution throughout cosmic history. Mergers will continue. The largest galaxies in each cluster will grow by consuming their smaller neighbors, drawn together by dynamical friction, the gravitational drag that slows massive galaxies moving through the cluster's population of stars and dark matter and causes them to spiral inward toward the cluster's center over billions of years. Over hundreds of billions of years, the member galaxies of each isolated cluster will merge progressively into fewer and larger systems, until eventually each cluster is dominated by a single enormous elliptical galaxy, the accumulated remnant of everything that once orbited within its gravitational reach. Star formation within these remnant galaxies will have largely ceased long before this merger process is complete. The raw material for building new stars, cold, neutral, hydrogen, and molecular clouds will have been consumed by the star formation of earlier epochs, and expelled by stellar feedback without replacement. The hot diffuse gas in the cluster halo will cool too slowly to provide meaningful replenishment. The stellar populations of these galaxies will age without renewal. Their youngest and brightest members, the massive blue stars that produce most of a young stellar population's light, dying out within millions of years and leaving behind successively older, cooler, dimmer stellar cohorts. What dominates the surviving stellar population over these immense timescales is not the blue giants or yellow main sequence stars like our Sun. It is the red dwarfs, the smallest and least luminous of all hydrogen-burning stars. Masses ranging from about 8% to 40% of the Sun's mass surface temperatures so low that they glow a deep red rather than the yellow-white of solar-type stars. Red dwarfs burn their hydrogen with extraordinary efficiency, consuming their fuel supply so slowly that their main sequence lifetimes extend into the trillions of years. A red dwarf with half the Sun's mass will continue burning hydrogen for approximately 5 trillion years, more than 300 times the current age of the universe. The faintest red dwarfs with masses near the hydrogen burning limit will shine for tens of trillions of years. These dim, patient stars will be the last fires burning in the isolated cluster galaxies as the universe ages into its far future. Planets may orbit many of them. On some of those planets, conditions might conceivably support chemistry complex enough to produce life or to sustain whatever life has evolved or migrated there from younger worlds. But the universe visible from those worlds will bear no resemblance to the universe visible from Earth tonight. A civilization living on a planet orbiting a red dwarf in one of these isolated island galaxies, existing perhaps 10 trillion years from now, would look outward through whatever instruments their civilization had developed and find a universe of extraordinary bleakness. Their own galaxy would be there, aged and dim, dominated by the faint red glow of ancient stars and the darker remnants of stellar evolution white dwarfs cooling toward invisibility neutron stars. Black holes accreted from the stellar populations of 100 billion years of galactic life. Beyond the galaxy's edge in every direction there would be nothing. No neighboring galaxies, no visible clusters, no filaments threading through the darkness. No cosmic microwave background radiation stretched by cosmic expansion to wavelengths longer than the observable universe itself, detectable by any instrument the civilization might conceivably build. The other galaxy clusters, the ones that once shared the cosmic web with their ancestors, will have receded beyond the cosmological horizon. The expansion of space between isolated clusters will have reached velocities exceeding the speed of light, not because any object travels faster than light through space, but because the space itself between clusters expands fast enough that the distance grows at a rate light cannot overcome. Photons emitted by a distant cluster toward the isolated galaxy will find the destination receding faster than they can travel, the gap widening with every meter of their journey. They will never arrive. They will be redshifted into silence, their energy dissipated across an ever-expanding void, their signal lost before it can reach any receiver. For the civilization in the isolated galaxy, the universe will appear to contain only what gravity has retained within their island. Everything else will be invisible, inaccessible, and after sufficient time, undetectable in principle. If those beings attempt to reconstruct the history of the universe from the evidence available within their observable horizon, they will find no indication that a cosmic web ever existed. No background radiation hinting at a hot, dense beginning. No neighboring galaxies suggesting a larger distribution of matter. No redshift surveys revealing the three-dimensional structure of the cosmos. They will observe a single aging galaxy adrift in an apparently infinite, apparently static, apparently eternal void. They will have no reason to suspect the universe was ever otherwise. This is perhaps the most quietly devastating implication of the void's dominance. It is not merely that the universe will become emptier, it is that the evidence of what it once was will become inaccessible. We live in a privileged moment, an epoch, when the cosmic web is still intact, the quasar from the Big Bang is still detectable, when the redshifts of distant galaxies still reveal the expansion of space, when the entire 13.8 billion year history of the cosmos is still written in the observable universe, in forms that careful instruments can read. That privilege is temporary. The universe is not static. It is not waiting for us to finish our observations before changing. It is evolving continuously, and the direction of that evolution is toward the erasure of its own history. The observations we make today, the surveys and maps and spectroscopic catalogues and microwave background measurements, represent a record that will not always be available. Future civilizations existing in the far future of an isolated island galaxy will not have access to the evidence we take for granted. The Big Bang will be for them not a well-established scientific fact, supported by multiple independent lines of evidence, but an untestable speculation about events that left no detectable trace in the universe they can observe. The cosmological principle, the expansion of space, the large-scale structure of the cosmic web, all of the framework within which we understand our position in the cosmos will be invisible to them, not because they lack the intelligence or the instruments to detect it, but because the evidence will have been carried beyond the horizon by the relentless expansion of the void. In this sense, the void is not merely a feature of the universe we inhabit, it is the fate the universe is moving toward. The 80 to 90% of cosmic volume already occupied by voids today will become a larger fraction tomorrow, and a larger fraction still a billion years from now. The matter concentrated in the filaments and clusters of the cosmic web, the luminous minority of the universe, will not disappear. It will not be consumed or destroyed, but it will be progressively isolated, divided into smaller and smaller islands by the expanding voids between them, until the connections between islands are severed entirely, and each island exists in a universe that appears to any observer within it to be empty everywhere except here. The universe is not moving toward more complexity. It is not building toward greater structure or richer organization. It built those things during the epoch we happen to inhabit, during the few tens of billions of years, when gravitational structure formation was competitive with dark energy expansion, and the cosmic web could be assembled and maintained. That epoch is ending. The great project of cosmic structure formation, the amplification of quantum fluctuations into galaxies and clusters, and the vast lacework of the cosmic web, has reached its peak. Everything that follows, measured across the trillions and quadrillions of years that remain before the last stars exhaust their fuel, is simplification, dilution, the patient, irresistible triumph of emptiness over structure. The void does not rush. It does not need to. It has already won the argument. The question of whether the universe is fundamentally a place of matter and structure with voids, as the incidental spaces between, or fundamentally a place of emptiness with matter as the temporary exception, was settled by the numbers before any human being existed to ask it. 80 to 90% of cosmic volume now at the moment of the universe's maximum structural complexity belongs to the void. 100 billion years from now, the fraction will be larger. 1 trillion years from now, larger still. The trend does not reverse. The arrow does not turn back. We are watching the universe at its architectural peak and calling it ordinary. We are standing inside the largest confirmed void in the observable cosmos and calling our position typical. We are measuring the expansion rate of a universe we do not fully understand from inside a gravitational environment that biases every measurement we make, and we are refining those measurements with exquisite precision without always asking whether the precision is masking a more fundamental uncertainty about where we are standing when we make them. These are not failures. They are the natural consequences of being finite minds inside an infinite cosmos, working with the instruments and the data available to us at this particular moment in cosmic history. The void does not diminish the achievement of understanding it. It deepens the achievement. Every measurement made from inside the KBC void that has revealed its existence, characterized its properties, and traced its influence on the expansion of space has been a triumph of the scientific method, operating under precisely the most difficult conditions it could face, measuring a structure from within it, detecting an absence rather than a presence, inferring the shape of a hole from the edge of the hole rather than from outside it. That achievement deserves to be held alongside the scale of what it revealed. Not to diminish the scale, But to insist that the scale, as overwhelming as it is, as resistant as it is to genuine comprehension, does not reduce the significance of the minds that measured it to zero. If anything, it amplifies it. The void is 2 billion light-years across and has been expanding since before our sun existed. The measurement that revealed its existence was made by 3 astronomers at a university in Hawaii using data gathered by instruments built by human hands over decades of accumulated effort. The disproportion between the measurer and the measured is one of the most remarkable facts in the history of science. And it is a fact that only makes sense if you accept that the universe, for all its emptiness, for all the darkness that fills its overwhelming majority, has produced in at least one corner of at least one void, something capable of looking outward and understanding what it sees. There is a reframing required before this ends. Not a gentle adjustment to the picture you have been building across the preceding hours, but a structural inversion, a demand that you discard the default orientation and replace it with something that the data requires but that the human mind resists with every intuition it possesses. The reframing is this: you have spent your entire life, and humanity has spent its entire history, treating the universe as a place defined by its contents: stars, galaxies, nebulae, clusters. The luminous structures that fill astronomical photographs and populate the catalogues of centuries of careful observation. When you picture the cosmos, you picture things, objects arrayed against a dark background, the background incidental, the object's primary. The darkness is where the universe is not. The galaxies are where the universe is. That picture is backwards, not metaphorically backwards, not backwards in some poetic or philosophical sense that invites debate, mathematically, geometrically, volumetrically backwards. The darkness is where the universe is. The galaxies are where the universe is not, at least not in any quantity close to what the word presence implies. The voids are the universe. The galaxies are interruptions in it, brief, luminous, structurally complex interruptions, the only interruptions capable of noticing themselves and asking what they are interruptions of, but interruptions nonetheless. The primary fact about the observable cosmos is not that it contains 2 trillion galaxies. It is that it contains a volume of space so vast. The 2 trillion galaxies, each holding hundreds of billions of stars, occupy only 10 to 20% of it. Consider what that fraction means concretely. The observable universe extends approximately 46 billion light-years in every direction from our position, a sphere whose volume is so large that expressing it in cubic light-years produces a number with more digits than this sentence has letters. Within that sphere, all the matter that has ever been observed, every galaxy mapped by every survey ever conducted, every star photographed by every telescope ever built, every atom of hydrogen and helium and carbon and iron that has ever participated in the story of cosmic chemistry, occupies between 10 and 20% of the available volume. The remainder 80 to 90% of all the space that exists within the observable universe is void, underdense, containing matter in quantities so far below the cosmic average that the gravitational forces required to build structure cannot operate effectively within it. If you chose a random cubic megaparsec of space in the observable universe selected with perfect mathematical impartiality and no bias toward any particular region, the probability that your chosen volume would contain a galaxy is between 10 and 20%. The probability that it would be void, underdense, devoid of any significant structure is between 80 and 90%. The most likely thing to find anywhere in the universe is nothing. The most likely cosmic environment is the void. The exception, the statistical outlier, the rare departure from the dominant condition is the galaxy. This inversion has not penetrated the popular understanding of the cosmos, and it has not fully penetrated the scientific one either. The reason is almost embarrassingly simple. We can only observe what emits or reflects light. Telescopes are instruments for collecting photons. Every photograph ever taken of the deep universe, every map ever assembled from spectroscopic surveys, every image that has shaped the public imagination of the cosmos shows only the places where photons originate. It shows you the exceptions. It shows you the 10 to 20% of cosmic volume where matter concentrated enough to ignite stars and build galaxies and produce the light that crossed billions of light years to register on a detector. The 80 to 90% that contains almost nothing produces almost nothing for the instruments to detect, and so it does not appear in the images. It is invisible not because it is hidden, but because there is almost nothing there to see. The Hubble Ultra Deep Field, perhaps the most famous astronomical image ever produced, shows approximately 10,000 galaxies crammed into a patch of sky no larger than a grain of sand held at arm's length. It is a genuinely extraordinary image, but it is also one of the most misleading images in the history of science, not because it is inaccurate, but because of the impression it creates. It suggests a universe overflowing with galaxies, so densely packed that they compete for space in the frame, so numerous that 10,000 of them fit into a patch of sky, barely distinguishable from nothing. The suggestion is wrong. Those 10,000 galaxies were found in that patch of sky because the Hubble Space Telescope was pointed there for 11 days, collecting photons from the faintest and most distant sources it could possibly detect. The image represents the result of the most ambitious light-gathering effort in the history of astronomy, and it shows you exactly what such an effort finds: the galaxies, the exceptions, the interruptions. It does not show you the vastly larger volumes between those galaxies, the supervoids and ordinary voids, and underdense regions that separate each luminous point from its neighbors by distances measured in hundreds of millions of light years. It cannot show you those volumes because there is almost nothing in them to show. If you could somehow give the void the same visual weight as the galaxy, if you could shade every cubic megaparsec of the observable universe with a brightness proportional to its matter density and display the result at the same scale as the ultra-deep field, the image would be almost entirely black. The galaxies would be barely visible faint specks scattered across an overwhelming field of darkness that would stretch to every edge of the frame without interruption. The universe would look at last like what it actually is. The origin of this architecture reaches back to a moment so early in cosmic history that the physics describing it operates at the boundary of what human mathematics can confidently address. Within the first fraction of a second after the Big Bang, before protons had formed from quarks, before the fundamental forces had fully separated from the unified state of the earliest cosmos, the universe underwent a period of exponential expansion called inflation. During this epoch, which lasted for an interval so brief that no unit of time familiar to human experience can meaningfully represent it, the observable universe expanded by a factor of at least 10 to the 26th power. Regions that had been in direct contact, close enough to exchange energy and information and reach thermal equilibrium with one another, were flung apart to distances that would require billions of years for light to cross. Inflation solved several deep puzzles simultaneously. It explained why the cosmic microwave background is so extraordinarily uniform in temperature across the entire sky, even between regions so distant that without inflation, they could never have been in causal contact and therefore could never have reached the same temperature. It explained why the large-scale geometry of the universe appears so precisely flat, the spatial curvature so close to zero that measurements spanning billions of light-years cannot detect a departure from flatness. It explained the absence of magnetic monopoles, exotic particles predicted by grand unified theories of particle physics that should have been produced abundantly in the hot early universe but have never been observed. And it did something else, something quieter and more consequential than any of these solutions. It took the quantum fluctuations of the vacuum and stretched them across the universe. Quantum mechanics, the framework governing the behavior of matter and energy at the smallest scales, dictates that the vacuum of space is not truly empty. Even in a perfect void, even in a region containing no particles and no radiation, the quantum fields that permeate reality vibrate continuously around their ground states. Virtual particles appear and annihilate in pairs on timescales too brief for direct detection. Energy fluctuates above and below the vacuum level in intervals governed by the uncertainty principle. These fluctuations are not mere theoretical abstractions. They produce measurable physical effects, including the Casimir force between closely spaced metal plates, and the Lamb shift in atomic energy levels. They are real features of the physical world, as confirmed and as precisely measured as any phenomenon in science. But they are fantastically small, operating at scales trillions of times smaller than an atomic nucleus, far below anything relevant to atoms or molecules or chemistry or biology, or any process occurring at scales larger than a subatomic particle. Under ordinary circumstances, they average to nothing, their effects cancelling over any volume larger than the quantum scale. They are the background noise of reality, always present, never consequential for anything we would recognize as a structure. Inflation changed that in the most radical way the universe has ever changed anything. The exponential expansion grabbed those quantum fluctuations and stretched them. A fluctuation, operating at a scale smaller than a proton, was inflated to a size larger than what would become a galaxy cluster. A fluctuation representing a minuscule excess of energy density in a volume smaller than an electron was amplified into a seed that would grow over billions of years of gravitational evolution into a filament containing millions of galaxies. A fluctuation representing a minuscule deficit was amplified into a seed that would grow into a void spanning hundreds of millions of light years. By the time inflation ended, these stretched fluctuations were frozen into the fabric of space as permanent variations in energy density. Tiny variations. 1 part in 100,000 from the cosmic means so small that no measurement of any kind would have detected them for hundreds of millions of years afterward, but permanent, indelible, written into the structure of space-time at scales that would eventually become the largest structures in the observable universe. The seeds of every galaxy cluster, every supercluster, every filament and wall of the cosmic web were planted in those first fractions of a second, and so were the seeds of every void. The seeds that became overdense regions grew by drawing matter inward. Gravity amplified their slight initial excess, pulling more matter from their surroundings, increasing the local density, strengthening the gravitational pull, attracting still more matter. The feedback was slow at first, operating over hundreds of millions of years before the density contrasts grew large enough to produce recognizable structures. But it was relentless. The overdense seeds grew into the first dark matter halos. The halos merged and accumulated gas. The gas cooled and fragmented into the first stars. Stars lived and died and enriched their surroundings with heavy elements. Galaxies assembled, clusters formed. The cosmic web emerged, its architecture, determined by the precise pattern of those original quantum fluctuations, amplified by billions of years of gravitational evolution into the grandest structures nature has ever built. The seeds that became underdense regions evolved in the opposite direction with equal inevitability. Their slight initial deficit meant slightly less gravitational pull. The neighboring overdense regions stole what matter remained, drawing it outward along the gradients of the gravitational field. The underdense seeds expanded. Their volume grew while their matter content shrank. Their density dropped below the cosmic average and kept dropping as the surrounding regions grew denser and the drainage accelerated. Dark energy rising to dominance over the last several billion years, as the density of matter diluted with cosmic expansion, while the density of dark energy remained constant, took over the dynamics within these expanding underdense regions and drove their growth with a force that gravity, weakened by the very emptiness it was operating within, could not resist. The largest void ever confirmed, the KBC void stretching 2 billion light-years around our position, began as a whisper of quantum probability in the first trillionth of a trillionth of a trillionth of a second. A fluctuation smaller than any scale human instruments have ever directly probed, occurring during an interval shorter than any clock has ever measured in a universe that did not yet contain the matter that would eventually notice it, existed. That whisper was stretched by inflation to cosmic scales frozen into the structure of space, and then amplified by 14 billion years of gravitational evolution into the largest coherent feature of our observable universe. Everything that followed from that whisper, every galaxy absent from the void's interior, every measurement biased by the void's outflow, every photon scattered differently by the void's underdense interior, every calculation skewed by the assumption that our location was typical when it was not. Every decade of cosmological debate about a Hubble tension whose resolution may lie in the simple fact of where we happen to be standing. All of it traces back to a quantum fluctuation that preceded matter, preceded atoms, preceded stars, preceded the Earth, preceded every living thing that has ever existed or will exist. The seeds of the void were planted before the universe contained anything capable of being affected by them, and they have been growing ever since. What does it mean to live inside the largest void ever found? Not scientifically, not in terms of its effect on the Hubble constant, or the peculiar velocities of neighboring galaxies, or the star formation rates of isolated void galaxies. What does it mean in the sense that any fact about your location in the universe can mean something to the mind that learns it? It means that the home you have never been able to leave is stranger than you knew. The cosmic address that felt like a minor astronomical detail, a particular galaxy in a particular supercluster in a particular corner of the observable universe, turns out to include a feature so large that it took humanity until 2013 to discover it, despite the fact that it surrounds us completely and has surrounded every human being who has ever lived. The void was always there. It was there when the first human beings looked up at the night sky and tried to make sense of the lights above them. It was there when Copernicus displaced the Earth from the center of the solar system, and when Hubble displaced the Milky Way from the center of the universe, and when every subsequent discovery pushed humanity further from the assumption of cosmic centrality. The void surrounded all of it. Every observation, every measurement, every photograph of the deep sky was made from inside it, filtered through it, biased by it. And the void is not anomalous. That is the final fact, the one that sits beneath everything else and gives everything else its weight. The KBC void is the largest confirmed void, but it is not a cosmic exception. It is a cosmic exemplar. It represents in extreme form what the universe looks like in the majority of its volume everywhere, at every scale above a certain size. The smaller voids that fill the spaces between galaxy groups, the medium voids that define the bubbles of the cosmic foam, the supervoids like Eridanus that leave their imprint on the ancient light of the cosmic microwave background, all of them are expressions of the same fundamental character of the universe. The universe makes voids. It prefers voids. It devotes the overwhelming majority of its volume to voids, and it is making more of them larger and emptier with every passing billion years. The galaxies we celebrate, the structures we photograph and catalogue and study, and occasionally allow to fill us with something that deserves to be called awe, occupy a minority of the cosmic volume so small that calling them the contents of the universe is approximately as accurate as calling the paint on the walls of a cathedral the contents of the cathedral. The paint is there. It is real. It is beautiful. It tells the story of the building in every detail visible to the eye. But it is not what the cathedral is made of. It is not what defines the space. The space is defined by the vast interior volume, the emptiness within the walls, the air and the light, and the silence that the walls exist to contain and shelter. The universe is the void. The galaxies are the walls, and the walls beautiful and complex and irreplaceable, as they surround an emptiness that is older than them, larger than them, and will outlast them by intervals of time that make their entire existence seem measured on the cosmic scale, like the brief flicker of a match struck in a dark room. The match burns. It illuminates everything within its reach. It reveals the faces of the people gathered around it, the features of the room, the texture of the walls, the depth of the space beyond. For the duration of its burning, it is the most important thing in the room, and then it goes out, and the darkness that was always there that surrounded the match before it was lit, and will surround the room long after the people in it are gone, reasserts itself as the primary condition. We are the match. The void is the room. But here is what the match illuminated, what the burning revealed before it is extinguished. It revealed that the universe, in all its overwhelming preference for emptiness, in all its vast devotion to the production of nothing, managed in at least one corner of at least one void to arrange matter into configurations of such extraordinary improbability that those configurations became capable of understanding the void that surrounds them. The emptiness produced against every statistical expectation, something that could measure the emptiness. The nothing generated in the thin, luminous exceptions to its dominance, the only things in the known universe capable of asking what the nothing meaned. That is not a small thing. It is perhaps the largest thing, not largest in the way the void is largest, not largest in terms of volume or mass or the number of digits required to express it. Largest in the sense of significance, in the sense of what it means that in a universe so thoroughly committed to emptiness in a cosmos that devotes 80 to 90% of its volume to the production of absence, in a void 2 billion light-years across that contains within it to a planet orbiting an ordinary star near the edge of an ordinary galaxy, there exists something that looked outward, measured what it saw, and understood that the darkness was not the background to the universe. The darkness was the universe. And the light, small and temporary and statistically improbable beyond any easy calculation, was the part that noticed. The void surrounds us on all sides, extending in every direction for 1 billion light-years before the density of matter begins to approach the cosmic average. It has been there since before the Earth formed, since before the sun ignited, since before the first stars illuminated the early universe. It will be there long after the last red dwarf exhausts its hydrogen fuel and fades to a cooling cinder drifting through the darkness. It is the dominant fact about our location in the cosmos and about the cosmos itself. But somewhere inside it, on a pale blue world orbiting an unremarkable star in the outer arm of an ordinary spiral galaxy, something lit a match, and for a little while the void was not entirely dark.